Category theory. Some of you might know it as a valuable part of your functional programmer's toolkits. Others might know it as scary nonsense that some people just won't shut up about. What you may not know is that applied category theory is an emerging field that is rapidly finding more and more use cases in all kinds of fields, in all kinds of areas of human endeavour. There's been an explosion of papers, conferences, research, industrial academic collaborations, and all kinds of things. And what it brings to all these different industries is a common language of compositionality, which is a concept that we're going to talk about a bit more here. To give you some idea of how brand new it is, there's one journal for applied category theory papers. It hasn't released its first issue yet. They're still working on it. There's one book. It was released last year. So this is really a cutting-edge kind of thing where new uses are being found for category theory in all kinds of different areas. Topics. So to give you a flavour of it, networks, thermodynamics, quantum physics, complex systems, natural language distributed systems, cybersecurity, music, digital circuits, data migration. These are all a very diverse grab bag of things. So what could they all have in common, I wonder? What about functional programming? Is that applied category theory? We could probably debate that. I'm going to say yes. For a start, we know that Lambda Man introduced monads to functional programming 30 years ago, which is part of category theory. His secret identity has since been revealed as Phil Wadler. It was Phil all along. Hooray. Thank you, Phil, for doing that. But also other kinds of functional programming, even untyped languages like Clojure and Racket, are deeply compositional in the nature of the work you do in them. And so I think it's a strong case to say it's applied category theory. So what I'm going to do, I want to put applied category theory on your roadmap. I want you to understand why I'm excited about it and why maybe it's something to watch as it develops over the coming years. We're going to look at the big idea of compositionality. If you come away with nothing else from this talk, I want you to understand something about that. We'll look at a cool case study. We'll go through a few concepts of compositionality and a couple of cool graphical languages. Compositionality, the definition that people go to most is attributed to Gottlob Frege, the German philosopher and mathematician in the 19th century. And it's something like, the meaning of a complex expression is determined by the constituent parts and the means by which they're assembled. In other words, if you know the parts by which something is built and you know the way that they're put together, there's nothing more to be said about the whole. And that's a really important thing. Maybe a punchier way of putting it is it lets us build big things out of little things, preserving guarantees. So does this sound like something you do for a job? Yeah, right? Does it sound like something many people do for a job in all kinds of different fields? Well, yeah, that's the point. So category theory is fundamentally the study of compositionality, and this is why it brings insights, or can bring insights to all kinds of different areas. So for instance, if we want to know how to make big programs that work out of little programs that work, whether we're making big electric circuits that work out of little electric circuits that work, big Feynman diagrams that describe valid particle interactions in particle physics from little diagrams that describe valid particle physics. And just by plugging them together, you know that it still obeys the laws of nature. Let's say you're the CEO of a logistics enterprise-y company with lots of trucks and planes and things, and you want to make big resource plans, working out what things have to go where, and you want to plug together lots of little resource plans in order to do that. Well, category theory can help you with that. Big networks of agents like police or government or military, networks of drones or something that work together, and you plug them together and you form a big network of things that work as well. So, to distill this idea to a concept that we can wrestle with, we need some idea of things that we're joining together, the building blocks by which we're building a bigger thing. And we need some idea of putting them together. So this most basic idea of compositionality is called a monoid. Now, I want to jolt you out of thinking about the Haskell type class monoid, which you might be familiar with mappend and mempty and all that sort of thing. That is one application of a monoid, but actually it's a much, much more general sort of concept. And here I want you to just think about building blocks, that we're building a big thing out of little things, whatever that might mean. So we'll say we have two things. We have some means of combining them into a bigger thing. And we need that operation to be associative. So don't need brackets. And that's the same. So there's no need to, that's unambiguous because of associativity. Now, do we need associativity though? Why is that jammed into the definition? Can it still be compositional if it's not associative? So I'm going to say that we do need it to be associative. This is very, very important because if it is associative, then that there is compositional. We know that we have A, B, and C, and we know how we're putting them together. That's all there is to know about A, B, C. But if it's not, then it's not enough. We also, apart from knowing A, B, C and how they're put together, we also need to know this external tree-shaped bit of data that describes how they're being put together, that this externality creeps in. And so it's no longer the sum of its parts. And also, we also want an identity element that is kind of blank and doesn't do anything when you compose it. So far, so good. Everyone clear on that? So we can generalize that. We can add a feature now and put colors on it so that you can't compose everything with everything. The colors have to line up before you do it. Now, this idea is called a category. And it's a generalization of a monoid. A monoid is like a special category with only one color. And that is the same category as in category 3. That's what the discipline is named after. Everything is built up out of this basic concept of compositionality, of being able to build big things out of little things. So once again, now terminology, the colors are called objects, and those building blocks that we're putting together are called morphisms. That's lingo that you'll see when people talk about category theory. Yep, composition, middle bit disappears, associativity and identity, same deal. This time the identities are colored. Cool. Does that make sense in the abstract? Well, we'll go into some concrete examples, of course. But as an abstract idea of just putting things together to build up a bigger whole. How's that? Yep. Alrighty. So let's look at a case study. This is a real case study. This is a research and industrial collaboration with John Byers and his team have been helping the US military develop a way of composing systems of systems. So the case study here is a search and rescue mission in the Caribbean where you have systems that all have to interlock to rescue people on this search and rescue mission. You might have UAVs, unmanned aerial vehicles, which are drones, helicopters, comm centers, bases, and all these things all have to click together. And so ideally, you would just be able to just click them all together and it all just works as one big whole instead of turning into a big unfathomable shambles, which is what often happens with military-style operations. So who are you going to call when you want to do that? Applied category theorists, that's who you call. So to start trying to dig out some concept of compositionality out of this domain, we can look at the graphs that represent how everything connects together. So here's one. We've got a helicopter, a port, and that it belongs to, and a target, which might be someone drowning in the sea, and we've got to go rescue them. And I've got different kinds of arrows here too. My port, that's like a static property of the helicopter. Comms range is sort of a dynamic property that'll change as things change. And intent to rescue is kind of like a plan that gets built up. It's a declaration of intent. And ideally, we want all these things to kind of connect together in a way that makes sense. So here's another network. This one now has a UAV, which gets launched from the helicopter with some other stuff. So one thing we can do is just overlay these. And the nodes in common just line up together and they click together like that. So that's a monoid right there. We had the helicopter network, the UAV network, and we clicked them together, overlaying them, and we got a combined network. So that's cool. That's a basic sort of element of compositionality we have. But it's not enough, because we need to sew together all kinds of different networks together, and we can't just all put them on top of each other. So here's an example. Here's another 3 networks, and we've got one with helicopters near the rescue scene and one with UAVs. It's kind of I made up the example. Or I adapted it from the paper that this is based on. And what we do, to get some sort of compositionality out of that, we can come up with this. It's kind of a template for sewing together networks. And there's 3 gaps here. There's for the 3 networks that have a particular number of vertices. So we can plug in a network with 3, a network with 2, and a network with 4 vertices, and then that will form a new network with 9 vertices. And it also overlays some extra relationships on top of it. So if we applied that to those 3 before, these ones, then we get this. So that's another compositional technique with the help of these sort of templates that help sew them together. Is that a category? It's not a category. It doesn't fit together quite like that. We need another concept. And so what we need is a morphism that has multiple inputs, because the multiple inputs here are those 3 things where you can plug in the networks. We can plug in a network with 3, a network with 4, and a network with 2 vertices. So they're sort of the colors in the morphisms that we had before. So this is now a new concept. It's a further generalization of the idea of a category, but you can have multiple inputs, and that's called an operad. Once again, composition happens in the way that you might expect. You click together the colored parts, and that forms a bigger one. So all of the inputs that didn't get used up are still there to be used. Then you have identities, and then they can plug in wherever you want. Here's a concrete example that we're all familiar with, types and functions. So here we can imagine a login function that takes a username and password as input and returns a user. A receive invoice that takes user, invoice, and signature and returns a receipt, and then store receipt that puts it in a shoebox. We could compose them together in the obvious way, and then that would form a new function like this that takes all of the parameters that haven't been composed in the middle, and you would get that pseudocode program there. So that's the idea of an operad. Now, returning to our use case, mapping that to a real sort of real situation. If we imagine these networks are actually there in the Caribbean with Havana as the port, and we want to sew them together so that they can all work together. So we apply that template, and they all get sewn together in one big network with all of the arrows that determine that behavior sewn together. Now, in practice, when you do things with operads in applied category theory, you want to transport it to another context where it's more useful than just this abstract setting. So you map it to the operad of types and functions, or sets and functions. And usually you map it there such that it has a lot more detail. So here, all of those things now have XY coordinates, and they have fuel and comms range and all these other things that are needed for that use case. So this is just a very, very shallow taste of that use case. The mathematical model they developed is a lot more powerful than what I've showed, and that could be in a whole talk of its own. But that's an example of how compositional techniques can be brought to bear to help solve problems, really very, very difficult real-world problems. I want to show you another thing. These are called string diagrams, and this is the design that we saw at the start of the talk. Is there anyone who can't figure out roughly what this is supposed to be doing? It's pretty straightforward, right? So this diagram precisely represents an underlying category. This is a visual language for displaying the compositional relationships between people. And depending on what category you use, you can describe very, very different things in these kind of diagrams. But crucially, they're just so intuitive that you can also, you can do all your hard work, and then many, many people can potentially read these diagrams. How to plug it into what we've learnt so far. The boxes here are morphisms. They're the building blocks that we're building up. The lines between them are objects. Now, it's easy to think of that recipe thing as types and functions, like it was a computer program. And this kind of flips around our intuition a bit, because most programmers are used to thinking of data structures as the boxes and the functions as the lines. But here it's the other way around. The functions are the boxes and the data structures they're data. They're just cables joining the things, which makes a lot of sense in a lot of contexts. And it's a useful way of thinking about it. Composition is just boxes being next to each other with lines feeding in. But there's another concept we need here. It's a little bit more involved than what we've covered so far. So there's this extra concept of tensoring, which lets us compose the objects together as well. So the wires, the tensoring sort of bunches together the wires that feed in as inputs. That's the extra bit that we need here. So this abstraction is called a monoidal category. It's a regular category plus this extra feature of tensoring that lets us join together the wires. It is a monoid. So the way that we join together those objects, that is a monoid itself in the way that they compose together. And so make lemon filling, for instance, if you look at make lemon filling, you can see it takes lemon, butter, sugar. And so the object there that's the input is lemon times butter times sugar using that operation. Technical definition, the tensor operation takes two objects into an object such that it's associative up to isomorphism, and there's a unit object somewhere that does nothing. So it's just a monoid. Happily, what this means for us in practical terms is we sort of have two-dimensional composition then. We can have horizontal composition where the building blocks follow each other, and that's just regular composition, and vertical composition where we can put them on top of each other using the tensoring operation. So for all practical purposes, that's what it means for us. It lets us put things on top of each other as well in these diagrams. There's another thing we can do here. We can put diagrams inside diagrams. They're compositional. And so we can put an extra, where it says make lemon filling, we can replace that with another string diagram that contains more stuff. And it just plugs in and more things there. And this is a really nice compositional property. We could take that and put it inside a bigger process where we're baking the pie as well. And that does what you think. So, surprise, it's another operator. If you're straining to see how it connects to that operator concept we talked about before, all of those boxes are the inputs to the operator, because you can plug more diagrams in there. The diagrams are the morphism, and we can plug them into these holes and build bigger ones. So that's that same compositional pattern appearing again, now in the form of these nesting diagrams. String diagrams are fantastic for software architecture. I've been using them to design software for 2 or 3 years, for as long as I've been reading about this stuff. And I also use them to teach software design skills to other developers. Because it's fantastic for describing the modularity and the layers of abstraction you want in software. You don't want to be having to look at all of your software at once. You want layers where you can just look at one layer and there's a few things. Then you look at the next layer down and there's a few things. And then you look at the next layer down and there's a few things. Well, you can't do that without compositionality. Otherwise it leaks. Software architect Simon Brown has popularized this C4 model for software architecture. And I doubt he'd know category theory from a bar of soap. But what he's come up with is this thing where you've got a high-level view of things, and then you can zoom in there, in that application, and there's more stuff in there. And then you can zoom into that one, and there's more stuff in there. And you can zoom into that, and then that collapses into code. Well, this looks very similar to an operator, doesn't it? It looks very similar to that same sort of nesting doll composition with multiple inputs that we saw with the string diagrams. And what you notice is that smart people tend to gravitate towards compositional designs because they're so elegant and powerful, even if they don't know about category theory. But then how much more powerful then to have these mental tools of reasoning about compositionality to start with, to guide your designs. There's one more thing I'd like to cover. The operative wiring diagram. So this is a similar diagram concept. This is another graphical language for representing compositional ideas in practice. And this time, it's circle-shaped, which doesn't mean anything. That's just a representation. But we see that the boxes, the things inside it, these circles, they're the inputs. We can nest the diagrams inside the diagrams. But now instead of having effectively a type signature of inputs and outputs, now there's just a bunch of loose wires and we have to cable together the wires. So the inputs there, they're the inputs of the operator. The wires, all the cables that are loose around each one are the input types, and the ones around the outside, the cables poking out of the outside, is the output type. And then you can compose them by plugging diagrams into diagrams like that, as long as you can cable the wires together. Do you need a minute to look at that, or is that, can you sort of see what's happening there, how we're plugging these wiring diagrams together? I'll hit you with a concrete use case taken from this paper, and that's compositional SQL queries. I think we've all used SQL queries before, and we all have a sense, perhaps, that there's some compositional nature to them that's a little bit hard to get at, usually. So we can use these wiring diagrams to describe them. Now here, the circles there are tables. Because if we imagine this diagram as a whole producing tabular data, then you can plug it into these table circles to produce, that's like having subqueries that generate tabular data that you could plug into the from clause. And also we have the constants, male and female in this case, which are also data that could be replaced by some sort of subquery or sub expression or something like that. The wires poking out of it is the select clause, because that's the data generated by the query. And if you were to plug that into a bigger query, that would be the data that gets consumed by that bigger query. And then the where clause is all the cabling that connects all the things together. So that's a really, really useful concrete use case, I think. And there's a bunch of other ones that are covered in this paper. What I hope to leave you with here is just how broadly useful it is to have a vocabulary of compositional concepts and how widely they can be used. So applied category theory is a really, really exciting new field. This abstract language of composition is something that can be applied in all kinds of different fields, and it's emerging in front of our eyes. It's still very, very early days, and we've barely scratched the surface of what it can do. In the future, really, anything where making big things out of little things is a thing that you do, and you don't want it to get all weird and complicated as you put them together. Well, this is something where applied category theory might find inroads. One in particular, in software development, I'm much more interested in category theory for things like software architecture and system design than I am for types and functions, which is the usual category that we use in our functional programming. So ops, for instance, I'd love to see it come to ops work, where we have running systems in production, and each one we add, it just seems to make everything worse and more complicated, and nobody can work out what is happening, and things go up and things go down, and nobody understands it the more things are in there. So this just seems like an area that's crying out for some compositional analysis. I'd love to see an academic collaboration with industry in that field in particular. But there's so many more things there. We can expect that software development will lead the charge because software is in everything these days. There's nothing that doesn't use software anymore. We've eaten the world. So we can expect to be at somewhere in the mix in this field as it develops. If you want to learn more about applied category theory, here's a bunch of cool people on Twitter. Most of them are mathematicians, and all of them are really, really friendly on Twitter and always happy to answer questions. The three at on the right are applied category theorists that are actually monetizing their work in a startup that's built around a visual process language based on applied category theory. And that's really exciting too. Further reading, so the book that I mentioned before, 7 Sketches of Compositionality, is a great place to start. And John Baez's lecture had a series of lectures on that. And yeah, this is all the materials I used for the talk. That's all, thank you.